Welcome to Genetics 101. We're going to go back to where we left off last time. We started with Mendel and looking at the different patterns of inheritance that he noticed, which was that there were dominant and recessive traits. He noticed that if you took true breeding, always, you'll understand what that means soon, parents of a dominant trait and a recessive trait, and put them together, that the first generation of children only showed the dominant trait. It was almost like the recessive trait had been lost. However, when you bred those children into a second generation, that recessive trait would pop up again. Mendel hypothesized that there must be a way for this information to be passed down from grandparents to child, without it being lost but hidden. Then we had other scientists investigating heredity after looking at Mendel's work in the 1900s. They found that there can also be other relationships like CoDominance, where there are two dominant traits which fight for supremacy, and in the end you have them sharing the organism. However, when you take those F1 generations and breed them, you then have a splitting of the traits again, where you have the dominant traits either showing up on their own or again as a codominant relationship. Finally, the other one that they were really looking at was incomplete dominance, where you have two traits which seem to mix and combine and make a third trait. However, when you take this generation of organisms and breed them, you end up having those traits pushed back to pure traits and mixed again. These relationships started scientists thinking, how is it that traits can be hidden? How is it that these traits can be mixed? It can only be explained if every organism has at least two pieces of information for every characteristic that they inherit. One piece of information given to them from their mother and one piece of information given to them from their father. This would explain these three relationships. Here's an easy way to think about it. We have a given characteristic, and it has many different traits or versions of that characteristic. So in the case of, say, the pea plants, you had seed shape, and that could have been round or wrinkled. That's the different traits, round or wrinkled. Now think of them as recipes for a certain characteristic with different versions, like a cake. We have a basic cake recipe that we all follow, but there are different versions of that cake, and they still follow pretty much the same steps to make a cake. There's only a few minor variations that make a big difference when you actually end up having the cake cooked. So simply adding cocoa to a cake mixture will turn it into chocolate, as opposed to vanilla, or banana instead. Now, what we do understand is that there are certain traits, like chocolate, that when you add them or put them in with a trait like vanilla, they'll actually dominate the mix anyway and take over. You put vanilla mix and a chocolate mix together, you're going to get a chocolate cake. This sort of thinking helped us to understand how these traits worked a bit better. Then we started to think that for all of these observations to be true and have traits skipping generations, that two copies of any recipe must be passed on to an organism. One copy of the recipe must come from their mother, one copy from their father. And if you think of it in terms of copies of recipes, that helps explain an awful lot of the observations we made. If you have two recipes, one from Dad, one from Mum, but one of those recipes is dominant and the other is weaker than the other one, say recessive, then this is the recipe that will show, and this is the recipe that, although is there, is hidden. However, when you go and have kids, if you pass one of those recipes on to one child and one on to the other, that recessive trait can then show again in those children if there's no other dominant recipe to take it over. If the next generation then receives a recessive recipe from both the mother and the father, then that means there's nothing else to dominate over it, and that recessive trait would then show. However, if the next generation has a dominant trait and a recessive trait given to them, then the trait will be hidden again. So this sort of thinking helped us to understand how we could get dominant and recessive traits, and it also explains codominant and incomplete dominance. If you end up with two different dominant traits that are fighting for supremacy, that would explain codominance, because one is given to them from the father, one is given to them from the mother, neither want to back down, so you end up having that both of those traits showing through. If you have two traits that are reasonably dominant but can't overwhelm each other, then you end up having a mixture of those traits coming through. So in the case of the red and the white flower, we had red and white combining to make pink, which, as we know in a paint palette, works quite normally. Then, if that generation then had children and gave a copy of those traits to their children, some of the children would end up with only red copies. Some of the children would wind up with only white, and some of them would end up with a red and a white copy, which would explain the red, pink and white observations that we made with incomplete dominance. Remember this? All of these three examples can be explained if you understand that there must be two copies of recipes for every characteristic. You receive a copy from your mum and a copy from your dad. It's how those recipes are in combination that gives the characteristic that you see. So now we're going to go over a little bit of what these characteristics are called, the terminology that we give to them, and how we actually explain the numerical patterns that we see to this data.